Hi there, and thank you for watching my video on confidence intervals for the mean, assuming normality. How to do it when sigma is known, when sigma is unknown, with or without Excel. Let's get to work. So how can we construct confidence intervals for the mean, assuming normality? First, we'll deal with the case when sigma is known, and then with the case when sigma is unknown. So take a random sample from a normal distribution with parameters mu and sigma square. And here we assume that this sigma is known. I know it's not very realistic because if we don't know mu, we typically don't know sigma either in real applications, but it's so much simpler to deal with this case first. So I will also denote the observations by lowercase xi. So these are the numbers, right? Our data. Now, a 1 minus alpha confidence interval for mu can be written in the following way. We have a lower bound and an upper bound. And in the lower bound, we have x bar minus a complicated term. And in the upper bound, we have the same x bar plus the same complicated term. So we shorten this notation by x bar plus minus complicated term within brackets. And let's deal now with the complicated term. We have this part, this sigma divided by square root n. And n, recall that n is our notation for the sample size. Now, what is the sigma divided by square root n? It's recall that xi has a standard deviation of sigma, so x bar, the random sample mean, has a standard deviation of sigma divided by square root n. So this is precisely the standard deviation of the mean of the random sample. And it is called standard error of the mean because it's the standard deviation of the mean of the random sample. Now, what is this z in pre-multiplying the standard error? Well, it's a quantile, but it's not the alpha divided by 2th quantile. It's the 1 minus alpha divided by 2th quantile of a standard normal distribution. So let's draw maybe the situation. It will be easier to understand this. So here is the standard normal PDF. And let me try to draw a standard normal PDF here. A nice bell-shaped PDF, right? Well, we know that the bell is located at 0. And let's take already alpha divided by 2 in the tail, an area of alpha divided by 2. So to get alpha divided by 2, I have here the alpha divided by 2th quantile, right? And, well, it's a symmetric distribution, right? So if I want in the right tail to have alpha divided by 2, then here I will have the 1 minus alpha divided by 2th quantile, right? Now, this is what my z measures. It's basically when I write z and subscript alpha divided by 2, it means that in the right tail I have an area of alpha divided by 2, right? It's shorter to write than with the quantile notation. So I will use this notation. It's a very common notation in statistics, z, and it's also called critical value. We will see more in general critical values later on. Now, let's take an example, how to calculate these z values, because so far it's a little bit abstract. I would like to apply this confidence interval to an example, but how to find this z value? Well, either using a table or using Excel. So maybe let's start with if you have access to Excel, this is how you will do it in Excel, how to calculate it with Excel. For example, when you have alpha equals 5%, well, you in the lecture slide, I wrote that with Excel you use norms inv, and you need to put a negative sign in front and specify alpha divided by 2 in parentheses. So let's open Excel. I write equals minus norms inv, and I specify, well, 5% divided by 2, it's 0.025, right? And so I get 1.96 basically, right? So z of 0.025 is 1.96. Uh, that's right. Now let's calculate it with a z-table. Well, with a z-table, we typically have the left areas, right? The red highlighted areas here. And the z in a confidence interval wants the right tail, the area in the right tail. So here, since in the table I have the left tail probabilities, instead of looking for 2.5%, I'm looking for 97.5%. In other words, 0.975. Where do I find it? Here I am. This is where I have 0.975. And the corresponding quantile is 1.96, right? Because it starts with 1.9 and the second decimal is 6, right? So that's precisely, it confirms what I obtained here, right? Now, let's go back to our lecture slides. How to, what are the most common confidence intervals in statistics? Well, typically the 90%, 95%, and 99%. I would say that 95% is the most common confidence interval, confidence level, basically, then followed by 99% and then 90%. So for these, if you can double check it with Excel or using a table, that we get these numbers and the corresponding confidence intervals, right? So let's consider an example. Here I have a data work junior exec. It's available on the course website, and let's open it. This is how it looks like. And these are, what are these numbers? These are weekly hours of working hours of junior executives. We have in total 50 observations. And I would like to calculate the confidence interval, the 95% confidence interval for mu by assuming that sigma is equal to 5. And we will do it both with Excel and without Excel. So let's start this time by doing it by hand using a z-table, right? So here it is. I would like to apply this this formula here, right? Let me take a snapshot. I would like to calculate this, right? And for our example, I know that X bar, I need X bar, right? I first of all need X bar. And X bar, I still use Excel as a calculator. Well, X bar, for the sample mean, it's average in Excel. And you enter the data. I get 60.232. So that's my sample mean. And sigma is given in the example. This is 5. And n, we have 50 observations here. So I simply need to calculate this. I get a lower bound of 58.84. You can double check my calculation. This is what I obtained as confidence interval, 95% confidence interval for the mean working hours of junior executives. And now with Excel, you can actually use confidence, right? In the lecture slides, I have confidence, alpha, sigma, n. But take care, Excel only provides basically a number when you type this. So this is the number that is provided in Excel. So this is with Excel, you use this confidence and you specify in parentheses the inputs. So let's calculate concretely this confidence interval. So equals confidence. And I specify my alpha is 0.05. Standard deviation was given it's 5 in this example, and sample size is 50, right? So I have 1.3859. So in order to calculate, so that's just the width, basically half of the width of the confidence interval. So to get the lower bound and the upper bound, I need to, so that's right here, the confidence interval. I need for the lower bound x bar, I calculated already x bar, here it is, minus this, and on the right I have x bar and plus this, right, what I got here. Here you go. So I got the same, basically the same results as with my handwritten calculation, right? And well, Excel provides a more accurate result. We have more decimals. Now let's do something more more sophisticated. In reality, we never know sigma, so how to deal with this situation? Well, the problem is that is the following. I do not know. I know that if I take the standardized random sample mean, so here I take away the hat in the sigma, I know that this has a standard normal distribution. But is it really the case when I replace sigma by its estimator, right? If I put a hat on top of it. Well, what happens? Well, it's more complicated. The problem is more complicated than this. I can actually use still the normal distribution, hence the standard normal quantize. I can almost do this. It's a tiny bit different. So what is the issue here? Well, the thing is that it does not have exactly a standard normal distribution, and the exact distribution has been derived by William Seeley Gossett. We see him here, and he actually worked in the quality control department of Guinness more than 100 years ago. And well, go figure why he only had access to small samples when working for Guinness, and he had to test the quality of the Guinness beers. And in small samples, he noticed that using the standard normal distribution for this random variable is not very accurate. So he worked during a couple of years, and he derived the exact distribution of this statistic. So when he actually published his result in 1908, he published the exact density of this statistic, and he actually did not. Guinness did not allow him to publish under his name, so he had to use basically a nickname. And since he was indirectly a student of a prominent statistician called Pearson, he used this student pseudonym to publish his result. So what is his result? If you take a normally distributed random sample and you standardize it, but in the denominator you replace sigma by its estimator, the usual estimator of the variance, right? Then it does not have an exact standard normal distribution, but a student t-distribution. It should be called Gossett distribution, but because of Guinness and Carl Pearson, we are stuck with student t-distribution. And so how does it look like? It has a very complicated form, and actually for what is important for us is that it has a parameter. It has a parameter. The parameter here is denoted by n-1. And n being the sample size of our sample, right? And what is important is that okay, it has a parameter, and even if we don't know the PDF, you can look for the very complicated form given in the student's article or on Wikipedia. You can actually not even write it in a closed form for all parameter values of n. Now, you can calculate it with Excel or any statistical software. The important part for us is that we have if you draw the density, the PDF, it looks like this. For if you take the student T with k degrees of freedom, we have what is the degree of freedom is the parameter. This is the parameter. It's called degrees of freedom. And so if this n minus 1 you denote by k, well, k equals 1 corresponds to this case. It's nicely bell-shaped, a little bit like the normal distribution. And when you increase k, it actually it converges to the standard normal distribution. And the limiting case, when k goes to infinity, it coincides with the standard normal distribution. So that's the important part for us. So for basically k, what is k? Is the sample size. Well, it's actually n minus 1. And when n increases, this really coincides with the standard normal distribution. But for small sample sizes, we have, what do we have? We have fatter tails, right? The pink one, this pink one is the standard normal distribution. And when k equals 1, for example, we have very fat tails, much fatter than in the standard normal distribution, right? And the expected value of student T random variable is 0, just like in a standard normal, and the variance has this form k divided by k minus 2, and it only exists for k larger than 2, and the expected value, same thing with the expected value, but for k larger than 1. Now, we really need, you can calculate, of course, the PDF and the CDF using Excel, using these commands, but we actually really need them. However, for the confidence interval construction, I need the quantiles. Why? Because now that I know that I have student T distribution for the random sample mean, standardized random sample mean, well, I need to replace the quantiles of standard normal by the quantiles of a student T. Otherwise, the confidence interval actually does not change at all, right? We still have this for the 1 minus alpha confidence interval for the mean. We still have the same form. The only thing that changes is instead of z, we have now t, and t takes this parameter n minus 1, otherwise we still have this alpha divided by 2, and here, instead of having sigma, we replace sigma by s being the sample standard deviation, right? And t, what is t? Is the equivalent of z in our previous confidence interval. Let's draw here again the PDF, but this time the PDF of student T distribution. So here it is. It also has a nice bell-shaped form, right? Here I'm drawing the PDF, the density of the student T distribution with n minus 1 degrees of freedom. So we said that it's centered at 0, the expected value is 0. And if for a confidence interval I need alpha in the tails, and so here I have alpha divided by 2. I evenly distribute, I evenly share alpha in the tails, and in the middle I have 1 minus alpha, right? And now what about to get back to my notation, to my T notation? Here I will yes, let's start with this one, because this was the before it was our z alpha divided by 2. Now it's our t alpha divided by 2, but I need to specify that I have a parameter, right, n minus 1, and then the alpha divided by 2, and here it's the negative, because it's a symmetric distribution, is the negative of this, right? And that's right. So we have the quantiles of a student T distribution. How to find them? Using a table and using Excel. Well, with Excel, we write TINV, and then we specify in parentheses alpha and n minus 2. So let's calculate it for alpha 5%. Well, we have that, yes, let's take, here we need n, right? So we say that n is equal to 5. Then my corresponding quantile will be n minus 1 is 4, and we have 2.5%, so 0.025. Let's start with Excel and then with the table. So with Excel, we said that we write TINV, and then I specify the probability. Here, take care is really the 5% that I need to specify, and then the degrees of freedom, which is 4. So I get 2.776, right? And now with a table, how can I obtain this with a table? Say that you are at a final exam and you would like to calculate this with a table. Well, this is how it looks like, a student table. In the table, you do not have probabilities anymore, but you have precisely the quantiles, and here you need to look for two tails, because we already here with the two-tailed confidence intervals, and I'm looking for the 1 minus alpha confidence interval with alpha equals 5%. So I'm in this column, and I go down until I meet 4 degrees of freedom. These are on the left. You see the degrees of freedom. So 4 is actually here. 2.776 is the number that I got with Excel as well. It's good that we confirm the same number. That's right. So now, how to concretely calculate the confidence interval? Let's consider an example. Here we have again the Work Junior Executive dataset, and we would like to calculate 95% confidence interval for mu, but this time without fixing sigma to 5. So let's calculate the 95% confidence interval for mu in this example. Well, the formula is, we said, almost the same as above, but I need to replace the z values by t values, right? And sigma by the sample standard deviation. Now, x bar, we already calculated x bar. This we know, right? We calculated above. It was 60.232. We know that the sample size is 50. We still need to calculate the sample standard deviation and the t value here. Now, n is, we said, 50. So the degree of freedom is 49. And yes, and what about alpha? Alpha, we said, is 5%. Now, if you try to do the t-table, you will actually not be happy, because 49 as degree of freedom does not exist in the table. We have 40 and 60. So you cannot calculate it using a t-table. You need Excel for this example. Now, in practice, if some people only have access to the t-table and they still need to calculate a confidence interval, there are two approaches. Either you average the two closest values that you have in the table. So these in here, these would be averaging these two numbers here, or by taking the closest degree of freedom, which here will be 2.2021. In any event, we will try to be as accurate as possible. We will use Excel. So here, this was already what we calculated before. That was the sample mean, right? And here it was the confidence level. We actually don't need this part. Let me just insert a column. And now the standard deviation, sample standard deviation, is STDEV. And you specify the data column. So that's our sample standard deviation. And now how about the t value? Well, we said that it's TINV I specify the probability, but really alpha, not alpha divided by 2. For tin, it's alpha that you need to specify. And then the degree of freedom, which is 49. And now we can build our confidence interval. We said that it's x bar and plus minus this t that we just obtained, right? We said that this was 2.01 and this was 5.95, if I remember it correctly, right? That's right. And now for the lower bound, we said that it's x bar, which is here, minus this t value times the sample standard deviation divided by the square root of 50. And same, almost exactly the same thing, but with a plus inside. So we have this times the sample standard deviation divided by square root of 50. Here you go. We just obtained our confidence interval. We are all happy. We made it. And it's more realistic than the previous one, right, in which we simply assumed that sigma was equal to 5. Why would it be? And the sample standard deviation is not 5, actually. So we have a wider confidence interval than above, right? When assuming that sigma is equal to 5 and using the standard normal quantize. All right, so that's what we obtained as confidence interval. And now we may wonder what happens if the data do not come from a normal distribution, right? What if the random sample is not from a normal distribution? Well, for this situation, there is another video that covers precisely this situation when we do not have normality. And thank you very much for watching. The course material is available on this site. Thank you.